Hi guys, this is the EdExcel AS Level Further Maths paper covering the Decision Maths 1 module, and it's from the October 2020 series. Question number 1. We've been given a list of items as shown over here, and for part A we have to use the first fit bin packing algorithm to determine how the numbers listed above can be packed into bins of size 8.5. Now, of course, with the first fit bin packing algorithm, we consider items in the order that they are given in. So for question number 1, we have our list of items and we need to use the first fit bin packing algorithm to pack these items. Now, I recommend you split your working into 3 sections for part A. So for part number A, we have 3 sections. In this section, we will label our bins. In this section, we will write down the contents of the bins. In this section, we will write down the space remaining in the bins. Now, of course, we need to open up a bin to begin the algorithm. So we begin with bin number 1. And bin number 1, that has space 8.5. We take a look at the 3.7 and clearly there is enough space in bin number 1. So we write down the 3.7 here, and therefore the space remaining, 8.5 take away 3.7, that's 4.8. So we have 4.8 over here. And let's mark this off. We now take a look at the 2.5. You can clearly see there is enough space in bin number 1 to place the 2.5 into it. So let's write down 2.5 here. And therefore the space remaining, 4.8 take away 2.5, that will be 2.3. Let's mark this off. Let's now take a look at the 5.4. Well, currently there is not enough space in bin number 1, so we have to open up a new bin. So we open up a new bin, bin number 2. Currently bin number 2 has space 8.5, and if we place the 5.4 into bin number 2, the space remaining in bin number 2 will be 8.5 take away 5.4, which is 3.1. Let's mark this off. Let's now take a look at the 1.9. Well, clearly there is enough space in bin number 1 to put the 1.9 into it. So we add in the 1.9 into bin number 1, and therefore the space remaining will be 2.3 take away 1.9, which is 0.4. So the space remaining in bin number 1 is 0.4. Let's mark this off. Let's now take a look at the 2.7. Well, clearly there's not enough space in bin number 1, and if we take a look at bin number 2, currently there is enough space to put the 2.7 into it. So we add in the 2.7 here, and the space remaining will be 3.1 take away 2.7, which is 0.4. So let's mark this off. Let's now take a look at the 3.2. Well, there's not enough space in bin number 1. There's not enough space in bin number 2, so we'd have to open up a new bin and put 3.2 into it. So let's open up a new bin, bin number 3. Currently, bin number 3 has space 8.5. If we put 3.2 into bin number 3, the space remaining will be 8.5 take away 3.2, which is 5.3. Let's mark this off. Let's now take a look at the 3.1. Well, there's not enough space in bin number 1. There's not enough space in bin number 2. However, there is enough space in bin number 3. So we can put 3.1 into bin number 3. And therefore the space remaining, 5.3 take away 3.1. That will be 2.2. So the space remaining in bin number 3 is 2.2. Let's mark this off. Let's now take a look at the 2.7. Well, there's not enough space in bin number 1. There's not enough space in bin number 2. There's not enough space in bin number 3. So we'd have to put the 2.7 into a new bin. So let's open up a new bin. We'll call this bin number 4. Bin number 4 has space 8.5 to begin with. And if we put the 2.7 into it, the space remaining, 8.5 take away 2.7, that will be 5.8. So the space remaining in bin number 4 is 5.8. Let's mark this off. Let's take a look at the 4.2. There's not enough space in bin number 1. There's not enough space in bin number 2. There's not enough space in bin number 3. However, there is enough space in bin number 4. So we put the 4.2 into bin number 4. And therefore the space remaining, 5.8 take away 4.2, that's 1.6. Let's mark this off. Let's now take a look at the 2.0. There's not enough space in bin number 1. There's not enough space in bin number 2. However, there is enough space in bin number 3. So we can put the 2.0 into bin number 3. And therefore the space remaining, that will be 2.2 take away 2.0, which is 0.2. Let's mark this off. We have now packed our items into 4 bins as shown. For part B of the question, the first fit bin packing algorithm is to be used to pack n numbers into bins. The number of comparisons is used to measure the order of the first fit bin packing algorithm. By considering the worst case, we have to determine the order of the first fit bin packing algorithm in terms of n. You must make your method and working clear. So for part B, the worst case is when every item is placed into a separate bin. Of course, when we begin our algorithm, we put the first number into the first bin. And this will leave space U in bin number 1. Now, for our second number, we compare this with the amount of space left in bin number 1, which is U. And because we're considering the worst case, of course, there is not enough space in bin number 1 to put the second number into it. So we place the second number into bin number 2. And of course, this will leave space V in bin 2. with our third number, we compare our third number with the amount of space left in bin number 1, which is U, and the amount of space left in bin number 2, which is V. So the third number is compared with U and V. So because there's not enough space in bin number 1 and bin number 2, we place the third number into a new bin, bin number 3. And of course, this will leave space W in bin number 3. Our fourth number is compared with the amount of space left in bin number 1, which is U. It's also compared with the amount of space left in bin number 2, which is V, and the amount of space left over in bin number 3, which is W. And again, because we're considering the worst case scenario, we would have to put the fourth number into its own bin, bin number 4. And of course, this will leave space X in bin number 4. And we can continue this up until the nth number. So when we can continue with the nth number is compared with U, V, W, X, etc. And of course, because we're considering the worst case, the nth number is placed into bin number n. And of course, this will leave space Z in bin n. Now if you go back to the question, we were told that the number of comparisons is used to measure the order of the first fit bin packing algorithm. So, of course, with the first number, there is going to be no comparisons. However, when we consider the second number, you can see here, we've compared the second number with the amount of space left over in bin number 1. So therefore, we have one comparison so far. If we consider the third number is compared with the amount of space left in bin number 1 and bin number 2. So therefore here, we've got two comparisons. And if we consider the fourth number, that's compared with the amount of space left over in bin number 1, the amount of space left over in bin number 2, and the amount of space left over in bin number 3. So you can see here, we've got three comparisons. Hopefully you can spot a pattern. For the second number, we've got one comparison. For the third number, we've got two comparisons. For the fourth number, we've got three comparisons. And therefore for the nth number, we would have n-1 comparisons. The number of comparisons is always one less than the number we're considering. So therefore, the total number of comparisons we've got here 1 plus the 2 plus the 3, and then we continue this up until the nth-1 comparison. And if we add all these together, of course here, this will be 1/2 n lots of n-1, which is equal to 1/2 n squared minus 1/2 n. And therefore, we can conclude we have the first fit bin packing algorithm being quadratic order, and that's because of this n squared term. Question number 2. A project is modelled by the activity network shown in figure 1. The activities are represented by the arcs. The number in brackets on each arc gives the time in hours to complete the corresponding activity. Each activity requires one worker. The project is to be completed in the shortest possible time. For part A, we have to complete the precedence table in the answer book. So for part A, here is our precedence table, and we've got the network shown here. Of course, this network is the same network as the one shown in figure 1. The only difference is the nodes have been replaced with these boxes, which indicate the early event time and the late event time. However, for the sake of this question, let's just treat these boxes as nodes. If we take a look at activity A, activity B, and activity C, you can see those are connected to the source node, and therefore there is no immediately preceding activities for A, B, and C. So we can indicate this with a dash. Let's take a look at activity D. You can see here, activity D depends on A completing. So here we write down A. And if we take a look at activity E, that depends on A finishing. So we write down A over here. Now, when we come to look at activity F, of course, activity F, that depends on B. What you can also see, through this dummy, activity F also would depend on activity A completing. So activity F is preceded by A and B. Let's now take a look at activity G, that's here. Well, clearly it depends on C completing. It also depends on B completing, and that's shown through the dummy over here. Now, we can't move on to do G unless A has also completed, and that's indicated by this dummy over here. So G depends on A, B, and C. And the same is true for activity H. We have A, B, C. If we take a look at activity I, that depends on D completing. If we take a look at activity J, well, clearly J requires E, F, and G to finish, so let's just write that down. Here we have E, F, and G. But also, it requires D to finish as well, and that's indicated by this dummy over here. And it also requires H to finish, and that's indicated by this dummy over here. So we have H over here. And if we take a look at activity K, that's this activity here, that depends on H completing only. So this is our precedence table. For part B of the question, we have to complete diagram 1 in the answer book to show the early event times and the late event times. So if we go back to diagram 1, first of all, let's add in the weight of the dummies, which we know to be 0. So we have 0 here, 0 here, 0 here, and 0 over here. So, of course, we begin with the source node. For the early event time, we would have 0. Let's work out the forward passes. So, here, we have 0 plus 5, which is 5. There's nothing else to consider, so let's just add the 5 in over here. Now, over here, we could have the 0 plus the 3. So let's just write that down. 0 plus 3, that's 3. Or we could have the 5 plus the 0, which is 5. Of course, we choose the larger one, which is the 5. Here, we could have the 0 plus the 4, which is 4. Or we could have the 5 plus the 0, which is 5. The larger one, that's 5. So we write down the 5 over here. Let's consider this. 5 plus 6, that's 11. Nothing else is going in, so we write down the 11 over here. Now, let's consider this box. We have over here 5 plus the 7, which is 12. Nothing else is going in. Now, for this box, there's various ways we can consider what goes here. We could have the 11 plus the 0, which is 11. We could have the 5 plus the 8, which is 13. We could have the 5 plus the 5, which is 10. We could have the 5 plus the 3, which is 8. We could have the 12 plus the 0, which is 12. The largest one, that will be the 13. And if we consider what goes here, well, we've got 11 plus the 8, which is 19. We've got the 13 plus the 9, which is 22. We've also got the 12 plus the 6, which is 18. And therefore, the largest one, that will be 22. Now for the late event time for this box at the sync node, we would also have 22. And now we need to work out the backward pass. So we have over here 22 take away 8. You'd find that to be 14. So let's just write down the 14 here. We've got the 22 take away the 9. That's 13. Let's just write down the 13 here. And we've got 22 take away the 6. You'd find that to be 16. Let's just write all those down here. Now, if we consider this over here, the only thing coming out of this is the J9. So when we come to work backwards, there's nothing else we need to consider, so we can write down the 13 over here. Now, if we consider this over here, what's coming out is the I8 and the dummy over here. So we've already considered how we got this 14. If we also work backwards, we have the 13 take away the 0, which is 13. Of course, the smallest one, that will be 13. So 13 goes over here. And similarly, over here, we've got the 16, which we worked out previously. Now, what's coming out over here is the dummy and this K6. So if we work backwards, we've got 13, take away the 0, which is 13. So the smallest one over here is the 13. Now, if we consider this over here, what's coming out is the G3 and the H7. So let's work backwards. So here we've got the 13, take away the 3, that's 10. And we've also got the 13, take away 7. This is 6. The smallest one, that's 6. And if we consider this over here, what's coming out is this dummy and also F5. So if we work backwards, we have over here 13 take away 5, which is 8. Or we've got 6 take away 0, which is 6. The smallest one, that's this 6 over here. And if we consider this over here, well, what's coming out is this dummy, the D6 and the E8. So let's work backwards. We've got 13 take away 6, that will be 7. We've got the 13 take away the 8, that's 5. And then we've got the 6 take away 0, that's 6. The smallest one, that's the 5. If we consider what's coming out over here, we've got A5, B3 and C4. So if we work backwards, 5 take away 5, that's 0. 6 take away 3, that's 3. 6 take away 4, that's 2. So here we've got 0. So this is our network showing the early event times and the late event times for part B. For part C of the question, for the first part we have to state the minimum project completion time and then listing the critical activities. The minimum project completion time, that will be 22 hours. And the critical activities, those are the activities with 0 float. So for the critical activities, we have A, we have E, and we also have J. And that's because if we consider our critical path, we go here, then we go here, and then we go here. Hence, these are our critical activities. For part D of the question, you have to calculate the maximum number of hours by which activity H could be delayed without affecting the shortest possible completion time of the project. You must make the numbers used in your calculation clear. So for part D, we need to calculate the float of H. So for the float, we've got the late event time, which is 13. We subtract off the duration, that's 7, and then we subtract off the early event time. So therefore the float, that will be equal to 1 hour. For part A of the question, we have to calculate a lower bound for the number of workers needed to complete the project in the minimum time you must show you're working. So what we have to do over here is add together all the different ways. So let's do that. For part A, we've got A, B and C being 5 plus 3 plus 4. Then we've got D, E, F, G and H. So here we've got 6 plus 8 plus the 5 plus 3 plus the 7, and we've also got the I, J and K, so those will be 8 plus the 9 plus the 6, and then we divide this by the minimum completion time, which is 22. So let's work all of this out. We have over here 5 plus 3 plus 4 plus 6 plus 8 plus 5 plus 3 plus 7 plus 8 plus 9 plus 6, and then we divide this by 22. So it turns out we get 2.909, etc. So here we've got 2.909, etc. We have a lower bound of 3 workers. Of course, we need to always round up for the lower bound. For part F, we have to draw a cascade chart for this project on grid 1 in the answer book. So here is our grid 1, and let's begin with the critical activities. We begin with A, that has duration 5. Obviously we're starting off at 0, and obviously the minimum project completion time is 22. So for our critical activities, if we add these in, we go up to the 22 as shown here. Then we begin with A, and that has duration 5. So here we've got A. Then we've got E, that's got duration 8. So that takes us up to 13. So here we've got E, and then we've got as well J, which takes us up to 22. So here we've got J. Okay, and let's just add on the line over here. Now let's consider B, that's got duration 3, and the late event time, that's 6. So if we consider what's going on with B, if we add this in, we've got over here going up to 6, which is over here, and we know already that the duration of B is 3. So here we've got B, and therefore this remaining bit will be float. So here is activity B. Let's now move on to C. That's got duration 4, late event time 6. So let's add this in. We have over here going up to 6, like so. And we know the duration of C is 4. So that is shown like this. So here we've got C. And then here we've got the extra float. Okay, so that's shown over here. So let's now move on to D. That starts at 5, duration 6, late event time is 13. So for D, it starts at 5. Okay, so it starts over here, and then it's got a duration of 6. So if we add this in for D, this will take us up to 13, which is over here. Okay, so let's also add the line from here up to 13 as shown here. And let's add on the vertical line. And we know D has got a duration of 6, so that takes us up to 11, which is over here, and this bit will be the float. Okay, so here we've got D, here we've got D. Now let's add on F. Starts at 5, duration 5, and that will take us up to 10, and then we finish at 13. So if we add this on, same thing again. This will be the same length. Let's add on the vertical lines as shown here. And then duration is 5. So that takes us up to 10 as shown here. So this is F. And let's add in the float. Here we've got F. Okay. So if we add on the next one, we've got G. Starts at 5, finishes at 13, and length is 3. So if we add this in, you can see here got the same length here. So let's add this in. Duration is 3, so this will take us up to 8 as shown here. So here we've got G, and let's add in the float. So here we've got G. Now we've also got H. Starts at 5, finishes at 13, duration 7. So we need to add on H. So H, that is going to go here, and we've got a duration of 7, so that takes us up to 12. Okay, so here we've got H, and then here we've got the extra float. Okay, so here we've got the extra float, so that's H. And then we've got I and K, which we need to complete as well. So I, you can see I, that starts at 11. So let's add this in. So 11, that's over here. So if we draw a line, okay, so from I, that's over here at 11, and it goes up to 22. So let's draw a line here, up to 22. Okay, so here is I, and it's got a duration of 8. So 11 plus 8, that's 19. So that will take us up to here. And then we've got this extra bit of float as well. Okay. So let's show that this here is I. So this is I complete. And now let's take a look at K. K starts at 12 and has duration 6. Okay, so if we add this in, we have over here, starting over here, ending over here somewhere. So here is K, and it's got a duration of 6, so that takes us up to 18. So 18 is over here. So this is K. And then we finish off over here. So here is K. And that's how we go about the Gantt chart. For part G of the question, using the answer to F, we have to explain why it's not possible to complete the project in the shortest possible time using the number of workers found in E. Now, if you go back to the question, we were already told that each activity requires one worker. That's quite important. Now, if we go to our Gantt chart, we know over here, we know A is critical, and E is critical, and J is critical. So after A is completed, D, F, G, and H, and E must be happening, okay? And if we go back to part E of the question, we calculate the lower bound to be 3 workers. So let's just write down some of this information. So from E, we found the lower bound to be 3, and therefore the number of workers required is to be 3. Now, of course, A is critical. So once A is finished, D can start, E must start, F, G, and H must be happening, okay, once A is finished. And that's in between 5 and 13. We can shift these around. Of course, when I talk about shifting around, we can start D, F, G, and H later. But between 5 and 13, all of these activities must be happening. So let's just write that down. So between 5 and 13 hours, E, D, F, G, and H must be happening, and you can see that from this diagram over here. And from this, we can actually find out the total time to complete these 5 activities, and from that we can find out the lower bound to complete these 5 activities. So the total time to complete these 5 activities, we've got 6 for E, we've got the so 6, 7, so we've got 8, sorry, 8 for E. We've also got the 6 for D, and then for F we've got 5. For G we've got 3, and then we've got the H, which is 7. So here we get 29 hours, okay? So what can we conclude from here? So what we can see from here then is as 29 over 8. Now the 8 comes from the between 5 and 13 hours. This result, of course, is greater than the 3. It's not possible to complete with the lower bound of 3 workers because this result obviously is greater than the 3. And obviously this came from here. Question number 3. For part A, we have to explain why it is not possible to draw a graph with an odd number of vertices of odd valency. So we know already that the sum of the order of the vertices is equal to 2 times by the number of edges. So what does this mean? This means that the sum of the order of the vertices must be even. Now, what this also means then is that you must have an even number of vertices of odd order. And the way to think about this is, if I have a couple of nodes over here, and let's suppose this one has 3, this one has 5, and this one has 1. Then here we've got 3 plus 5, which is 8, plus 9, which is 9. So this is odd, but we want even. Now if I have, say, I don't know, a 7 over here, then because I've got 4 even, I've got 4 even vertices of odd degree, that means the total over here must be even, because an odd number of odd vertices is will be odd. So this would imply that you must have an even number of odd vertices, because if you have an odd number of odd vertices, then you'd have the sum being odd, which is impossible according to this statement here. For part B of the question, figure 2 represents a network of 14 roads in a town. The expression on each arc gives the time in minutes to travel along the corresponding road. Prim's algorithm, starting at A, is applied to the network. The order in which the arcs are selected is AD, DH, DG, FG, EF, CG, BD. It's given that the order in which the arcs are selected is unique. Using the information given over here, we have to find the smallest possible range of values for x, showing it working clearly. So let's draw our minimum spanning tree. We start at A and then we go to AD, okay? So that's this one over here. Then we have DH, so that's this one over here. Then we have DG, that's this one over here. Then we have FG, so that's this one over here. Then we have EF, that's this one over here. Then we have CG, so that's this one over here. And then we have BD, that's this one over here. So how does this help us? Well, if we think about it, what we're saying over here is this over here must be bigger than this over here, and it also must be bigger than this over here, because had we selected this, then here we would have got a cycle which we're not allowed for a minimum spanning tree. So what this means then is, for part B, the 2x plus 10, this is greater than the 3x minus 2, and what it also means is that the 2x plus 10 is greater than the 20. So if I solve this inequality, we've got 12 being greater than x, And if I solve this one, we've got 2x being greater than 10, and therefore x is greater than 5. So let's just write this down as a whole solution. We've got x, which is in between 5 and 12. Now for part C, a route that minimizes the total time taken to traverse each road at least once is required. The route must start and finish at the same vertex, so this implies we need to use the Chinese postman algorithm. And given that the time taken to traverse this route is 318 minutes, we have to use an appropriate algorithm to determine the value of x, showing it working clearly. So here we've got a copy of figure 2, and what we can do first of all is work out the order of the vertices. So here we've got 2 for A, B we've got 1, 2, 3, 4, C we've got 1, 2, 3, E we've got 1, 2, 3, F we've got 1, 2, 3, H we've got 1, 2, 3, G we've got 1, 2, 3, 4, 5, 6, and D we've got 1, 2, 3, 4. Okay, so what we can now do is write down the odd vertices. So for part C, the odd vertices, okay, so for the odd vertices, we have C, E, F, and H. Okay. And now we need to find out the pairings. So for the pairings, we've got CE, so starting at C, finishing at E. Well, the shortest way we can get there is, well, we could go 42, or we could go C to G, so that's 15, plus the 23, so 15 plus 23, you'd find that to be 38. And then here we've got 15 plus the GF, so we're adding on 10. And then we add on the 12, so that's 37. So one other way we could have gone there is 15 plus 10 plus 12, which is 37. So CE, that's 37. And then we have FH. So let's find out the quickest way we can get from F to H. So F to H, we could go 29. Another way we can go there is the 10 plus the 17, which is 27. Or we could go 10 plus the 8 plus the 7. So that will be 25. So the smallest one is 25. So here we've got 25. Okay. So let's just get rid of these annotations. So if we add these together, it turns out we get 62. So that's one pairing. We could also have CF. Okay, let's just open up the brackets for now. And then we've also got EH. So let's work out how we can get to C to F in the quickest way possible. So C to F, we could go 15 to 10. So that's 25. Or we could go the 42 plus the 12, that's longer. So the quickest way is going to be 25. And E to H, starting at E, finishing at H. Well, we could go E to F, so that's 12. Then F to G, so that's 22 so far. Then to D, so that's 30. And then plus the extra 7, that's 37. That's the shortest way I can spot. So adding these together, 25 plus 37, that's again 62. And then another way we can get there, sorry, the final pairing will be CH, and then we've got EF. So CH, starting at C, finishing at H, we could go to G, and then we could go to D, and then we could go to H. So here we've got 15 plus 8 plus 7, so that's going to be 30. And then E to F, starting at E, finishing at F. Well, that's quite obvious, that's just 12. So therefore, adding these together, we get 42. So we would therefore have to repeat CH and EF. So let's add this to our diagram. So we need to repeat CH. So let's add this over here. We need to repeat this. And we also need to repeat EF. So we need to repeat this over here. So CH, we've just found that to be 30. And here we've got the 12. So therefore, we know that the total time is 318 minutes. We were told that in the question. And the way of the modified network, that will be the 5x plus the 246. So this comes from the original network. And then we add on the 42, which is from here. And we know that this is equal to the 318 as described in the question. So here we've got the 318 minutes, which is why we've got this over here. So if we tidy this up, 5x is equal to 30, and therefore x is equal to 6. Question number 4. Figure 3 shows the constraints of a linear programming problem in x and y, where R is the feasible region. Figure 3 also shows an objective line for the problem and the optimal vertex, which is labelled as V. The value of the objective at V is 556. We have to express the linear programming problem in algebraic form, list the constraints as simplified inequalities with integer coefficients, and determine the objective. So we've got a copy of figure 3 over here in the answer book. Now, a couple of ways we can do this. One way is to first of all find out the equations of these 3 lines. So for that, we need over here some coordinates to consider. Now, it's always easy to figure out what's going on with integer coordinates. So here we've got the integer coordinate 0, 12, and here we've got the integer coordinate 6, 0. For this line over here, we've got the 0, 12, and then here we've got the 10. 0. And if we consider this line over here, consider integer points, we've got this point over here, which has got coordinates 7, 2, and then this point over here, which is 9, 8. Okay, so with this we can find out the equations of all three of those straight lines, and from that we can find out some inequalities. So let's first of all consider this line over here. If we consider the point 0, 12 and 6, 0, the gradient, that's equal to 0 take 12 over 6 take 0, which you'd find to be minus 2. The y-intercept, of course, that's equal to 12, and therefore the equation of the straight line, that's y equals minus 2x plus 12, which if we rearrange, we've got 2x plus y equaling 12. So let's label this. This line over here has equation 2x plus y equals 12. And let's call this equation number 1, just in case we need it later on. Let's now consider the points 7, 2 and 9, 8. So if we consider the points 7, 2 and 9, 8, the gradient, that's equal to 8 take away 2 over 9 take away 7, which is equal to 3. So therefore the equation of the line, we're going to have y minus y1, so we've got y minus 2 equals 3 lots of x minus x1, so we've got x minus 7. So we've got y minus 2 equals 3x minus 21. So if we tidy this up, you can see here, we end up with 3x minus y equals 19. Okay. So we'll call this equation 2, and let's add this to the diagram. This straight line over here is 3x minus y equals 19. Let's now consider this line over here. So let's consider first of all the points 0, 12 and 10, 0. Of course, the gradient, that's equal to 0 take away 12 over 10 take away 0, which is minus 6 over 5. The y-intercept, this is equal to 12. So therefore, we've got y equals minus 6 over 5 x plus 12. So if I multiply through by 5, we've got 5y equals minus 6x plus 60, and therefore we end up with 6x plus 5y equals 60. We'll call this equation number 3. So if I add this to the diagram, we have over here 6x plus 5y equals 60. And you can see v is the interception of 6x plus 5y equals 60, and 3x minus y equals 19. So let's write that down. We can find v by solving equation 2 and 3 simultaneously. So if we go to our calculator, we have a simultaneous equation with two unknowns. We've got 3x minus y equals 19, and then we've got 6x plus 5y equals 60. So therefore, we'll end up with 155 over 21 for the x coordinate, and the y coordinate, that's 22 over 7. So that's the coordinate of v. Now let's consider the objective line, okay? So if we consider the objective line, here we've got a coordinate of 0 across 5 up. Here we've got a coordinate of 3 across 0 up. So let's consider the 0, 5 and the 3, 0. The gradient, that's going to equal 0 take away 5 over 3 take away 0, which is minus 5 over 3. We know that the y-intercept is equal to 5. So we've got y equals minus 5 over 3x plus 5. 3y equals minus 5x plus 15. And therefore, we end up with 5x plus 3y equals 15. Now, of course, over here, this isn't what we want to maximize. This is just the objective line, which happens to be parallel to the objective line. So therefore, we need to recognize that our objective function is of the following form. So the objective function is of this form over here, and we wish to maximize this over here. Now, of course, the gradient of this line is parallel to this. So p equals k lots of 5x plus 3y is what we want to maximize. And we know already from the question that the maximum value is 556. And this occurs at the point V. So the maximum value is 556, and this occurs at V. So we can substitute all these in to find out what k is. So, in other words, we've got p, which is 556, which is the maximum value. This is equal to k lots of 5 times by the x coordinate, which we've just found to be 155 over 21. Okay, so here we've got 155 over 21. Plus 3 times by 22 over 7. So let's find out what k is. So here we have 556 over 5 times by 155 over 21 plus 3 times by 22 over 7. So it turns out here k is 12. So therefore, k equals 12, and therefore we have the objective function that's given by p equals 12 lots of 5x plus 3y, which is the same as 60x plus 36y. So therefore, we want to maximize p equals 60x plus 36y, subject to the following constraints. Now, here, remember the shaded region is the region we don't want. So if we consider the 2x plus y equaling 12, we want the region which is not shaded, so the 2x plus y must be greater than the 12. So that's one of them. So here we've got the 2x plus y being greater or equal to 12. Then we've got if we consider the 6x plus 5y equaling 60, we want the bit that's not shaded, so here 6x plus 5y is less than or equal to 60. So here we've got 6x plus 5y being less than or equal to 60. And then if we consider the other one, we want everything above the line. So here we've got 3x minus y being less than or equal to 19. So here we've got 3x minus y being less than or equal to 19. So let's just box all this. These are our constraints. Okay. So this is our final answer.